Today we're going to be working out an area. Now this is what we call an irregular area because the shape of it is not really a nice rectangle or a nice square or a nice circle. It's just kind of this weirdo looking shape here. It's not even a polygon, it's got curvy edges and straight edges over here. So how do we approach this thing? You can see I've outlined this shape and all the information in between about trees and this basketball court and the paths and so on. We can factor that in later. We're just going to consider this first big outline shape and work out its area. So if I just consider the actual shape itself, this is what we've got. Now, we did approach this as, in our first case, as a set of composite shapes put together, okay? So you could divide this up however you like. You can see there's like a big rectangle that will fit in here, and you can put different spaces around here. Now, keeping in mind that we're going to be estimating this, it's not going to be exactly correct. We don't have to have every single little nook and cranny calculated. The simpler we can make this for us, the better. So what I've done is I've put together this set of composite shapes. You can see that all I've got really is three rectangles. I've got one big rectangle here, I've got a smaller rectangle and another smaller rectangle, and that's it. You might say, man, that's terribly inaccurate. You know, I'm missing heaps of pieces on this. And that's kind of true, but if you have a look, say for instance this rectangle over here, you can see that this rectangle is bigger than the area that I'm trying to calculate. It's got these extra spots over here. But at the same time, what I've got is other spaces within the area that I haven't calculated. So I'm kind of estimating and making these extra bits try to balance with the bits that I'm missing. It's a little bit like the trick you can do if you're adding a bunch of numbers. For instance, I'll just put this down here. If I said, please add 14 plus 47 plus 12. Okay, well, I could just actually do all the numbers on these and do it exactly or punch it into a calculator. But I can say this is going to be approximately equal to, and I can round all of these numbers and see what I get. So 14 would round to 10, 47 would round to 50, and 12 would also round to 10. So this is going to be approximately equal to 10 plus 50 plus 10, which is 70. Okay. Now if you actually go ahead and check what this is equal to, 14 plus 12 is going to be 26, and when you add that to 47, I think you're going to get 73. So clearly, I'm in the ballpark. I've got something that's roughly right, and I can use this approach of, you know, sometimes rounding numbers up and sometimes rounding numbers down, and everything should sort of come out in the wash, and I'll have a reasonably close answer. So what I've done is, in order to work out the areas of these rectangles, clearly I'm going to need some measurements. Okay, so I've taken my ruler out and I've done this all in centimeters. These are the numbers that I've gotten. Now you can see here I've got my my long edge of this big rectangle here, 14.9, and its corresponding breadth is 8.4, and then I've done all the other measurements. Okay, now we know how to do the areas of rectangles. They're really easy. All you have to do is length times breadth. Then you do length times breadth again, length times breadth again, and you'll have three areas. I've just put together a quick table that shows you what happens when you go length by breadth. That gives you one rectangle, another rectangle, and this is the biggest rectangle here, and this is what they add up to. Okay, now it's worth mentioning, all of these lengths here, right? These are all centimeters, and so are these. Which means that these over here are centimeters squared. Centimeters squared. Now, we know that the area we're doing is not centimeters squared. It's going to be meters squared. It's a much bigger area. So what I need to do is I need to work out a scale. I need to work out, well, what are these meant to correspond to in real life? So I'm going to come back to my diagram. What I've got over here, if I come back to the original, is that I went and I took this satellite photo and I measured from here to here with my ruler. Okay. Now the length that I ended up calculating, measuring out, was, well, let's see here. No, I've got a bigger one over here. I might use this. Okay. So when I place this ruler across, I measure 16.7 centimeters. Okay, all the way from here up to here, 16.7 centimeters. Now I can use my satellite photo to find out what that measurement is in meters. And what I find is, according to the satellite photography, that my 16.7 centimeters is supposed to be equivalent to 105.63 meters. Okay, so in order to work out, translate this into meters squared, I want to know what 1 centimeter is. So if I divide both sides by 16.7, what you'll end up getting is about 6.33 meters. Now, there's a tricky thing here because this is a length, and I'm interested in an area. So it would be an easy thing to say, oh, okay, therefore 1 square centimeter will be 6.33 square meters. But that's actually not quite right, because 1 square centimeter, if I just put this over here, we write it like that. What it really means is literally a square with 1 centimeter over here and 1 centimeter over here, 1 by 1. And so it's really 1 centimeter times 1 centimeter. And that's why the ones come together and the cm, the units come together, and you get 2 of those, okay? But this key is that it's a square, right? It's a square. It's 1 centimeter by 1 centimeter. So if I had a square like this, 1 centimeter by 1 centimeter, then it should be equivalent to a square that's got these dimensions instead. It should be 6.33 meters times 6.33 meters. That's a bit sneaky, isn't it? 1 square centimeter is not 6.33 square meters. 1 square centimeter is, in fact, if you crunch the numbers, I got 40 meters squared, give or take. Okay, this is roughly equivalent. Okay, so this is great. I can take this value here and I can multiply it by 40. And if I just reach for my calculator now, I'm going to get 151.27 times 40. So I'm getting an estimated area of about 6,000 square meters. Okay, so this is one answer that we've got, and the method we used was composite areas. So the first approach was to break this shape, this weirdo looking composite figure, into many different sort of like a rectangle and another rectangle and another rectangle, or whatever other shapes you would like to combine. But the other way we're going to do is using Simpsons Rule. So Simpsons Rule approximates this in another way, and it uses a different formula. Now, the approach is going to be quite different. We're going to need to divide up the shape across a diagonal, and by the way, it doesn't have to be this diagonal, it could be like another diagonal over here or any other diagonal you like. And then across that diagonal we're going to break up this shape with some lines that cut the diagonal across and divide up the entire area into a bunch of shapes that we can then compare. So I've already done this, and then what you do with this shape is you need some measurements. Okay, now before we do the measurements and put them on there, one thing you should note is that these lines, they're not random, okay, these 3 lines that go across. For starters, you can probably see they're all perpendicular to our diagonal there, okay? The diagonal is really important because everything kind of branches off of that. This diagonal, not only is it perpendicular to all of these, but the diagonal is broken up into chunks, 1, 2, 3, 4, that are all equal to each other. And because you can see the way I've drawn it, these kinds of distances, it's kind of like a height. So this distance, which is the same as all of the other ones, we call the height, or we can call it h. Okay, so we're going to refer to that distance. I've already done all of my measurements, so I actually know that, for example, the height, it's equal to, for example, this one here, just to make it a bit easier to read, is 4.4 centimeters. You've also got this distance across here, which is 7.3 centimeters. This distance across the middle, 9.8 centimeters. And then this last one, the longest one, is 12.1. Okay, now, what do I do with all of these pieces? I'm going to need to throw them into this special formula that Simpsons Rule has. And with that, once I have a piece of paper, and the formula for Simpsons Rule goes like this. It starts with that height that we were talking about, which we'd measured as 4.4 centimeters. The area is approximately equal to that height divided by 3 times, and I'll explain this part in a second. You've got the first width across, you've got 4 times the middle width, and then you've got the last width. Okay, so when I'm talking about widths, what I mean is on the diagram, you can see you've got the heights going this way, and you've got the widths going this way, okay? Now, you can see this requires 3 widths, and I've got a whole bunch more. So what I'm gonna do is I'm gonna divide this into 2 pieces. I'm gonna take this part here, so if you like, it's going to be this area, and I'm going to work that out so you can see there's a first value, a first width, which in fact is 0. I've got a second width across there and a third width. And then I'm going to work out this area up here as a separate piece. So I'll put some dots on that. So this area up here, I'm also going to have a first width, a middle width, and a last width. So we'll call this one over here A1, and we'll call this A2, and we can work them out in order. Okay, let's give this a go. A1, it's approximately equal to, and my height is about 4.4 divided by 3. And then I'm going to punch in these 3 numbers that correspond to the widths here, right? So the first width I mentioned is 0 because I'm kind of starting at this point here, plus 4 times the middle width, which is 7.3, plus the last width, which is 9.8. Okay, now, when you throw this into your calculator, what you'll find is you'll get 57.2, and I'm doing this in square centimeters at the moment. I'm going to repeat the process for the top area up here, A2, okay? The height is the same, it's still 4.4 divided by 3, but my first, middle, and last are now completely different numbers. This is first, then middle, and then last. So I'm going to have 9.8 plus 4 lots of 12.1 plus the last one, which is 0, because again, just like I started, I'll end at a point up there, which is width, like that width there is actually 0, okay? Again, punch that in, and the number I calculated was 85.36 centimeters. So therefore, when I total these up, what I'm getting is 142.56 centimeters squared. Just like before, this is not, you know, this is not the actual size. I'm going to be in meters squared. I'm going to multiply by 40, right? So when you do that, you're getting approximately 5,700 square meters, okay, which you can see is in the same ballpark as what we worked out before. They're not the same because we've used a completely different method to get these answers, but at least we know our responses are sort of similar. We're on the right track here. Okay. Now, one of the great things about Simpsons Rule, even though it looks a lot more complicated, is that it's a lot easier to increase the level of accuracy you've got. If we went back to this shape over here, the way that we would increase the accuracy of this is we would consider smaller and smaller shapes. So for instance, I could have done this triangle over here. I could have chucked in another rectangle, maybe another rectangle in there, and so on. And the more I've got, the more accurate my shape will become, and the more accurate my area will become. Now, I can do a similar kind of trick with Simpsons Rule. What I'm going to do is, I've still got the same diagonal, but instead of having 1, 2, 3 widths measured across, I'm going to add more. So, I've already done the measurements on this one. You can see I've got my original 3 here. 1, 2, 3 that I've highlighted. But then I've added in a whole bunch more. In fact, I've got twice as many. So instead of my height being 4.4, this distance here, my height is now 2.2. So this is substantially smaller. Each of these chunks is going to be more accurate because you can see, just like with the composite figure, I'm dividing it up. And when you go through the same process like this, but you're going to go through it many more times, what you'll find is that the total area in square centimeters, it comes out to, I believe it's 152.533, that's in centimeters squared. So when I work out my actual area, which is multiplying by 40, I'm going to get 152.533 times 40. So I'm looking at 6101.32 meters squared. That's 6,100. So this is great because we can see that all of the answers that we've got were in the same ballpark, but we can get more accuracy as we need it, right? Now, I guess our last step from here is then to consider, well, all we've worked out is just this big outline shape, right? This figure in pink. But there's basketball courts to remove. This particular picture is not going to be very useful to golf because this basketball courts have been they've been changed since this satellite photography was taken. We've also got paths happening in here, and also if we went up to the site, we can see that some of these areas, they're covered in benches and other kinds of things, which really should be taken away from our final figure. But all of these are methods you can use to, with quite decent accuracy, calculate an irregular area.